Well, can we get Gizem to code the Fibonacci? So I guess the problem is to code the Fibonacci function where it takes in a number, n, and then outputs the nth Fibonacci number. So you could do this in like a text editor or VS Code, whichever one you prefer. Also, you're muted, and can we get you to share your screen?
Oh, sorry about that. Yeah, I'm gonna share my screen.
Or
Um,
think out loud, and if at any point anyone has any suggestions or wants to jump in, feel free to do so as well.
Can you type out in the chat what the actual challenge is
Yeah.
for? I'm trying to remember exactly what you said.
Fibonacci numbers, right?
Yeah.
So what were the Fibonacci numbers? Can we
Oh,
put
I
those
forgot
on the
to
chat?
find that. Here, I'll type the prompt in the chat real quick. So Fibonacci and
Mhm.
return the nth Fibonacci number. So I believe to start off, the first one would be 0. The second one would be 1. I'm typing out the pattern in the chat as well. Second Fibonacci number is 1, and then after that, the next Fibonacci number is the sum of the first two. So the next one was fi minus 1 plus fi.
Something like that.
Yeah, exactly. Yeah, that's the first few. Cool. So then your program would take in a number and return the nth one. So if the input was 5, then the fifth number of that sequence, I guess we do 0 index. So 0, 1, 2, 3, 4, 5. The answer would be 5 if the input was 5. Does that make sense to everyone?
Yeah. Okay. So you're putting in the index number.
Yeah.
Okay. Do you want me to do it in a text file?
Actually, we could just do it here in this file, and we could
Here,
probably run it.
there? Okay. Do you want me to do Python or JavaScript?
Whichever one you're more comfortable with. I personally prefer Python, but it's up to you.
Python. But this is JavaScript.
Yeah.
Well, never mind then.
If you'd like, you could go to the recursion challenge file and then just add the function to the bottom.
Oh, and to the bottom. Okay.
Yeah.
Are we trying to make a recursive solution for this?
Yeah.
Oh, yeah. Okay. Why am I getting this here?
Because there's nothing written there.
Oh,
When you
so I
tab it
just
in and
say
you type
class.
something, it'll go away. It should go away. Yeah, there you go. Why isn't it going away?
See, if you hover your cursor over the squiggly, it might tell you what the error is. Oh, maybe you need actual stuff on that line. Maybe you type pass again, but don't press enter. Oh, never mind. It's like we could just ignore it for now.
Nothing.
Cool. So can you tell us out loud what the first step would be?
Okay. If we're doing recursion, I guess we need to know the base case.
Mhm.
Um, um, and the base case is when we reach to the last index.
Yeah. And
I
which
guess
one's
that's
the
where we
last?
need to stop.
Mhm.
Um, well,
So one thing to think about, are you counting up or counting down with your indices? Like if I give you
up.
number 5, are you gonna calculate Fibonacci 5, 4, 3, 2, 1 or 1, 2, 3, 4, 5?
I would go from the bottom because I have to add up my numbers. I need to know the first two in order to get the next one,
Yeah, that's an idea.
right? Um,
So similar to like the counting up problem then?
okay.
Yeah, well, we'll need another default variable next to IND that basically says count equals 0 on line 43.
Oh, you think that's going to be the input as well, or
Yeah, so
just behind?
right next to IND on line 43,
Mhm.
comma, space, put you can make a count, or to make it make sense, put index.
Oh, so like the first one should be,
And then equals 0.
okay, cool. So you want to rename it to index equals 0.
Yeah. No, not IND. IND is going to be the input, right? So that'll track like 5. As in, like, you need to find the 5th number.
Okay.
Yeah, so
Yes.
leave IND as, or you said IND because that's the index.
Yeah. Yeah.
Okay, so
Put
put,
it up. Mhm.
yeah, I was gonna say, okay, you could leave it as index and then just put count equals 0 then. So count will always equal 0 until in our function here, we increment it by 1 and then we run the code again. So our base case would be if index equals count, then we return whatever the number is, I guess, that we're trying to track.
Um. Okay. I don't know. Um.
Does anyone have any suggestions on the condition for the base case? Like what do we put in the if statement?
Can you remind me what our argument is in this? What does it represent?
So it sounds like index is the input that I give you. So if I say calculate the 5th Fibonacci number, index would be 5. And
Okay,
then
got it.
count is a number, yeah, that we're going up from 0, 1, 2, 3, 4, 5.
I would agree with what Sean said then, if index equals count.
Yeah, I put it in chat.
So if index equals count, return the Fibonacci number.
Right, because that's what we're trying to find, correct?
Mm-hmm. And then now the problem becomes how do we actually find that Fibonacci number that we want to return? So I have a suggestion from Megan. I think he accidentally sent it to me in DM, but it says, should we check if it's 0 first?
Yeah.
Oh, you want to edge case it basically.
Let me check if it's 0. So this looks like our base case is now when we're at the smallest index. So maybe we're thinking of a different approach now, where when we've reached the bottom, that's our base case. And when we're at the top, we like decrease the index until we reach the bottom. Yeah, that's awesome. And then the two base cases, because Those are the two that don't depend on the previous answer. Yeah, the everything else case. So we're not at 0 and we're not at 1. Let's say we're at 5. What numbers do we need in order to calculate the 5th Fibonacci number?
I guess I need to create an array and put those numbers in an array, reconstruct an array here.
Let's see. If we look back at the definition of Fibonacci, right?
Mm-hmm.
The current one is the sum of the previous two.
Yeah.
So at the 5th one, we're taking the sum of the 4th number, the 3rd number.
Mm-hmm.
So how would you generalize that to an arbitrary index? So if I'm at the ith Fibonacci number, how do I use the previous two to calculate the current one, right?
Yeah. So I should do that without an array? I can get that?
That's one way to do it, to build your answer from bottom up, to populate the array from index 0 to index n. But I think there's a cleaner way to finish our solution just within our else branch. And if anyone sees it, please shout it out.
Just going off of what you put in the chat at the beginning, where it was f equals f I minus 1 plus f I minus 2
Yeah, exactly.
there.
Mhm.
At some point I should do this, I guess, but
Yeah, you're exactly correct. So we're calculating the one at index,
oh
I'm
shit.
just gonna say I for index. So you want to use the Fibonacci, you want to use fib I minus 1 and I minus 2 and add those,
Mhm.
right? We're actually, yeah, exactly. Nice.
Mhm.
Cool. That's good. And I guess we can discard line 47 because we changed our base case to be once we've reached the bottom instead of once we've reached the top.
Mhm.
And now we're
Mhm.
counting down instead of up.
Okay.
Yeah, awesome.
Then I don't need this anymore either. Yeah.
Yeah, because we didn't count up anymore.
Yeah.
Yay. Anyone have any questions about the approach or the solution itself?
I mean, I'm not following it at all. How do you go backwards without knowing the previous one? You're going from 5 down
Yeah, so if we
to
look at
0, finding your index value.
so on line 54, right? If we start at 5, then we're assuming the function already works, and we've calculated the solution for Fibonacci 4 and Fibonacci 3. So we're assuming the function works for fib 4 and fib 3, and then we add those together to arrive at our answer for fib 5. Or let's see. Would it help if I stepped through a solution?
Yeah, I would need that because this is not making sense to me.
Cool, sounds good. Let's see, I'll do it in a Google Doc. And then screen share that. Cool, I'm gonna take over this screen share. So, Gizem, can you stop your screen share?
Yeah. Mm-hmm.
Maybe. There we go. Cool, so our solution was roughly, it's like fib n, right? And if n equals 0, return 1, I believe. And then if n equals 1, turn 1.
Yeah,
Or
those are the edge casings, right? Just to like,
Yeah.
if you get those that low hanging fruit, just return it.
Yeah, and then otherwise return the sum of the previous two, right? N minus 1 plus fib n minus 2. So this was roughly our solution. Cool, so let's say I told you to calculate fib 5, right? So if we step through the code, we step through the branches of the if statement. So Is it 0? No. Is it 1? No. So we returned this. So what we returned is fib n-1 would be 4, and then n-2 would be 3. Well, but we don't have like our answers for Fibonacci 4 and Fibonacci 3 yet. So then the program would have to calculate each of those individually. So first they would calculate fib 4, and then it would call this function, right? And then go through the branches. So it's not 0, it's not 1, so it returns the next one. So it returns Fibonacci 4 minus 1 is 3, plus 4 minus 2 is 2. Cool. And then we don't know what fib 3 is yet because this is just a function call, so then it would make this function call. So fib 3, it's not 0, it's not 1, so it goes to the recursive case once again. So we're doing fib 3 now. And it returns fib 2 plus fib 1. And then now we're at fib 2. Okay, I don't think I'll be able to go through all the recursive calls in this example actually, because after we do the first argument, we have to go back and calculate fib 3, fib 2, and fib 1 over again. But continuing this branch, we're at fib 2 now. That's not a base case, so we return fib 2 minus 1 is 1, plus fib 0. Cool, so now we're at fib 1, and that is a base case, so it returns 1. And then goes back up the stack. So now we have our answer to here, right? We have our answer to this fib 1. Whoops. So it returns 1 to here. And then now it needs the answer to fib 0. So it goes to calculate fib 0. It does that function call, and since we're at the base case, we get 1. So now back to here. It returns 1 up to here. And then this return was to this call of fib 2, right? So now if this gets replaced with 2, and now we have to calculate this fib 1. So it does that function call. We're at the base case, it returns 1. So now we have our answer 3 to this call of fib 3. And then we just keep going up the call stack until we found all our answers and like filled in all of those. Does that make sense? No?
No,
Are there
not
like
for me.
particular questions about it?
Honestly, I don't know what questions to ask to try and make sense of it. I'll just have to run through it later, I guess, on my own.
Yeah.
It looks like witchcraft to me right now.
She's just explaining what the computer is doing to get the returns, right? So she's going down the ladder as the computer runs the loop and then coming back up.
Yeah, so I was just breaking down. Like in order to do fib 5, we did this recursive case. And then within this recursive case, like there's more recursive cases within it. Because each of these fibs, like the first fib might call Fibonacci within itself, and then this one also, since it's recursive. Yeah, and then once it like returns an actual number, like here it returned 1 because we're at the base case, you can go back up the tree and replace that function call with that number. So like once I've calculated fib 2 using the program, it would replace this with the answer that returned, which would be 2, I guess. And it goes further up the stack by replacing fib function call, or the function call with the number that it calculated. I don't know if that made any sense. Julius, do you have anything to add to my explanation? Help clarify.
Well, not really right now. We'll cover it in a bit again. I do have a slide or two on it. Yeah, I think for the most part, it looks like you and the class and everyone has a grasp on recursion. And maybe if we just go over it a few more times and apply maybe a framework to it, we could really just kind of speed up the stickiness of every step to it. So what I really like what you're doing here, Phil, is because you're breaking down like what's happening at each iteration, and we're kind of starting to see like a pyramid-like pattern here, right? And that's kind of one of the key things about recursion. It's that it's ideal for these hierarchical structures where you have a lot of nesting, as opposed to iteration and loops, where you're more so dealing with flattened data. When you're dealing with an iteration, you could think of it as like going down a checklist of things, whereas dealing with recursion is more like dealing with nesting, when you have folders within folders within folders. Okay. I like visuals. I think some visual aids might help. This is a very good um, way to visualize it when we're doing the equations. I think we got.
You're not muted.
Oh, sorry. What happened?
Just a hot mic.
Okay, cool. Yeah, the visualization is good, and we could take that visualization a step further with some color coding. So with that, let's hop into today's recursion part 2. I am going to share some slides. And okay. All right. Are we seeing this all right? Cool. Sure, I have the Zoom thing up here so I can see everybody's chat.
What is your name again, sir?
My name is Julius.
Julius. Thank you.
Yep. All right, let's see. Yeah, we normally have like what is it called? Fixed days, which I think might make it less, or might make it a little easier to remember all of our names, but we're doing like this rotation thing this time, so no instructor is stuck with Saturday all the time. Let's see. We have, okay, we're at 8:37. We are pretty much on track here. We finished a few code demos and a very good example by Phyllis. So let's start with our slide deck. All right, so you're already a little familiar with recursion. At its core, it's really about seeing the big picture by zooming in on smaller, more manageable pieces. So imagine having a problem that's too big to tackle all at once, like untangling a ball of yarn or cords or whatever. Instead of ripping it apart, you want to start at the ends and work your way towards the middle. To understand recursion, one must first understand recursion. I don't know if this is a real quote, probably not, but it's a fun one. And I forget where this one comes from, but it is through recursion that we can wrap our finite minds around the infinite. Basically, recursion is a very beautiful practice, magical, mystical practice that happens throughout all of nature. And we see it in things like fractals, for example. And we'll talk about a few specific fractal algorithms in a bit as well. So recap. What is a recursive function? Anybody shout it out in your own words.
The function that calls itself.
Exactly. It's a function that calls itself to solve a smaller piece of the same problem. And in computer science, this is known as decomposition, or more colloquially as divide and conquer. So you take a problem, you split it down into subproblems, and you iterate from there. So what are cases in a recursive function?
You have your base case and recursive case.
Exactly. Your cases are essentially conditions in the function, and the base case is where the function knows to stop, whereas the recursive case is every other case beyond that. If we can continue to break it down, it's a recursive case. If we can't break it down any longer, or we have reached a solution we are looking for, that is very likely our base case. And here's a visualization of what that might look like. If you're trying to print an I statement and you're trying to reach less than 1, you're done when you reach this base case. Otherwise, you iterate through the recursive cases. And that's what this will look like in code. And that's what we just saw Phyllis demonstrate a second ago. So why learn recursion? This one's a little more open-ended. So let's hear some thoughts on this.
So you can learn memoization.
Hey, I really like that one. Yes, it's gonna come in very handy during the React portion. Memoization is great. Not easy to grasp at first, but it will come in handy later on. What else?
Sometimes it can like condense code.
Yes, definitely. It can make some very clean, elegant looking code. All right, what else?
Avoiding for loops.
Yeah, that is a reason, avoiding for loops. For loops, nothing against for loops. They serve their purpose here and there. They could be a little rudimentary. All right, so those are all very good reasons. Let's see if we have a few more. This one's I think useful. It can apply to virtually anything, right? The more techniques you learn, the wider range of scenarios you'll be prepared for. Algorithmic thinking. It also trains your brain to think in patterns, which is a big goal here at Platoon, because we want to get you all in front of employers and ready for whiteboarding challenges. And we want you to be able to feel confident that you can work through all of that and land your cushy dream job. Also, contrast creates clarity. So while for loops might be rudimentary, knowing for loops alongside of recursion allows you to see the pros and cons of each. They might reach the same goal in the end, but by taking a different path. And it's foundational to higher concepts, just like memoization, but also like maybe wilder stuff like the Sierpinski triangle, the Coach Snowflake, Conway's Game of Life. The Sierpinski triangle, I'm sure you've all seen it before, especially if you are into games like Legend of Zelda. It's created by recursively subdividing a triangle into smaller triangles. And Coach's Snowflake is basically the repetition of adding smaller equilateral triangles to each side of a shape. And if you haven't heard of John Conway's Game of Life, it's a really, really wild, what does he call it? A cellular automaton, I think. It's this wild concept created by a British mathematician, John Conway, back in 1970, so over 50 years ago now. While Conway's Game of Life isn't a recursive structure in itself, recursion can really help one understand the evolution of the states within Conway's Game of Life over time. So, like I said, it is foundational to a lot of crazier, wilder stuff. Now, let's talk about some pros and cons. I think a few of you have already mentioned some, like for recursion, basically we have the possibility for more elegant, clean code. Pro of iteration and loops as an alternative would be maybe a more straightforward linear control flow. It might take more lines of code, but it may be easier for a beginner to understand. And sometimes that's useful, right? Like it depends on, I think I might have said this before, might be obvious, but wherever you land, wherever job you land, there's going to be some kind of standard or practice in place, and that's a practice that you're going to follow. Some places, some employers might appreciate intelligent, witty code. Some other employers might prefer simpler, more rudimentary code that's easy to read, code that's quick and fast to read. Especially useful if you have very large code bases and you have people that have to jump in between all these different code bases. It's just simple is more efficient in that kind of case. What else? Hierarchical nested structures are suited by recursion. Flattened structures are more useful for iterations and loops. And again, the difference between this would be like folders within folders within folders, or the branches of a tree when we're talking about nested structures. And with flat structures, we're talking about like a flat list, like a recipe for cooking a dish. You just have a sequence of steps that you follow in a very linear fashion. Okay. We also have kind of very similar to the last one. Recursion's ideal for self-repeating tasks where you have the same problem to be solved at each step. Whereas with iteration, it may be a similar problem, but not quite exactly the same problem. And you could visualize this as a spiral staircase versus a traditional staircase. Now, some cons to each of these. The way recursion works is it is more demanding on memory because of a call stack, the call stack being just how the program or how the interpreter and compiler will handle temporary memory, the cache of current memory. With iteration, you could maybe run into that same issue if you were to start nesting for loops, for example. So iteration is really ideal for more straightforward cases, but sometimes you really just cannot avoid nesting. And when you're going with an iterative solution, this is when it becomes less performant. Because your code is more elegant with recursion, your iteration is more prone to complexity and code bloat. Because recursion utilizes more memory, it's more prone to stack overflow. And finally, recursion can be a little more abstract, so harder to understand at first. And again, iteration can be a little more rudimentary. Some of these are very subjective, of course, so just understand the differences of each and become more and more familiar with each. This is pretty much something you already know. I don't know why I named them as laws of recursion, but basically, since the algorithm calls itself, every iteration can be thought of as being the same case. The base case being the simplest, and every case beyond that being the recursive case. I guess I think that's the easiest way to think about it. And the steps that you've already been walking through, there are maybe techniques to help memorize it, right? I like steps. I like to break things down into frameworks. I think things like is it alliteration when everything starts with the same letter? That is a technique to help things be a little more digestible, easier to memorize. This also very much kind of mimics the scientific process, right? So there's a part where you're like collecting data and then you're hypothesizing. But basically, you start with, as we all know, identifying the base case, and that's your starting point. And then you want to, from the base case, be able to see the big picture. And you do this by gathering the data, listing the initial cases, and developing a trend between these cases. From there, you could shrink and break everything down. You compare the harder cases to the simpler cases, trying to uncover a pattern that you can translate into an algorithm, right? And once you see that trend that you're trying to create a pattern out of, you just give more and more structure to it, right? You're going to convert it into a formula and then an algorithm, and then you test for consistency. And once you have that consistency, you just clean up your code. And that is how you solve for recursion. Okay, examples. If you're not familiar with this classic problem, it's called the handshake problem. In a room full of people, how many handshakes are needed for each person to have shaken everybody else's hand exactly once? So, like, let's say there was a party. Every time somebody enters the party, they have to greet everybody else that's already there. Now, what else can you extrapolate from this? You don't have to shake hands with yourself. Nobody does that, right? So if we were to identify the base case, let's actually just hear some thoughts. Does anyone think they can come up with a base case on the spot for this?
If there's 1 people in the room, then there's 0 handshakes, and then if there's 2 people, then 1 handshake. I guess that's the base.
Exactly. Yeah, that is perfect for a base case. And one thing I do want to kind of point out here is I like that you said both, actually. I really do like that you said both of those as part of the base case, and we'll see in a second why. But when it comes to the base case, what you're really trying to do, right, is you're trying to identify a starting point. And it's not necessarily always so black and white. Any of these individually can essentially be your starting point. If it serves your use case, it's serving your use case. Give yourself some flexibility when you're identifying your starting point or base case. You could always adjust later if you need to, but usually there's more than one way to solve a problem. And in this case, you could either take any one of these as the base case or combine a few of them. In this example, we're looking at 1 being our base case. Basically, like you said, if we have only 1 person in the room, there are 0 handshakes, unless you're crazy and you want to shake hands with yourself. And so we return a 0 once we reach that point. Otherwise, well, I'm just kind of jumping straight into the solution here. So I probably should not have included that. We'll talk through it a bit more in depth in a sec. But let's look at the other scenario. Like if we were to include, or if we were to start with 2 as the base case, we're essentially combining 2 of the base cases mentioned before to cover our edge cases or our base cases. If there is 2 people in the room, we return 1. Otherwise, for whatever reason, if there are less than 2, then we return 0. In a case like this, as we iterate down, the algorithm would stop once we reach 2 people. But what if somebody decides to call this method and they pass in 1 or 0? And that's why we have this else if. So as to cover edge cases like that. It may not be how we intend the function to work, but as engineers, you will learn that people are very creative and have like just a knack for using things the way they were not intended to be used. So you always want to be able to cover edge cases. Okay. We could also be a little creative and take something like what we saw on the slide before and maybe for whatever reason, we want to get rid of the else if, which only serves to cover the edge case and have a more elegant looking solution. In this case, we have a function max, which will take the higher of these 2 values. So if our case was 2 minus 1 equals 1, that's what's going to be returned by this function. Otherwise, it's going to return 0 for either 0 or 1. All right. Like I said, we jumped straight from step 1 to step 5. So let's back it up a bit and let's talk about steps 2 through 3. Step 2 is seeing the big picture and gathering data and exploring as many cases as you need in order to identify the trends. And what that looks like here is in a room of 3 people, person A will shake hands with persons B and C. Person B then shakes hands with C. And if we elaborate on this, with 4 people, D enters the room. So now A is shaking hands with B, C, and D. B shakes hands with C and D, and C shakes hands with D. And we can now continue to visualize this. We're taking it in a more linear fashion now. We're starting to look at it with numbers rather than like just abstract words. And we see that we're starting to see some patterns here, right? Does anyone want to take a stab at calling out the pattern? Might kind of still be hard to put into words, but if anyone is so bold as to try. Yeah, I'm not even sure how I would articulate this pattern. Maybe it's, again, it's a word problem. It's kind of hard to extract a pattern out of at the spot. So maybe we got to like take it a step further, right? And let's restructure how we're visualizing this. So taking what we were looking at before, we start to replace our words with something a little more formulaic. And we see that as we expand, we have this pyramid kind of pattern occurring, right? And we can take this a step further by color coding it. And now we'll really start to see what's going on here. Every time we increase the number of people in the room from 0 to 1 to 2 to 3, this is the pattern that emerges. What's in green is basically the number of people in the room minus the person who has just entered. So when we have 2 people, it was 1 person that was in there prior, right? When we have 3 people, there were 2 people in there prior, so on and so forth. And what that means then is the pattern that we could uncover from this is there are that many handshakes as well. Whenever a new person enters the room, the number of people there before is the same number of handshakes that has to be added to our total sum of handshakes, right? And so the pattern that we uncover is n minus 1 plus the previous iterations. So handshakes of n minus 1. Does that make sense? And it's okay if it doesn't. If it doesn't make sense, let's start to poke some holes at it. Anyone want to take a stab or share their thoughts?
All right, just a quick question. So for starting at handshakes 2, that's when you're adding the n minus 1, right?
Mm-hmm.
And then are you like, how are you having the outside numbers on the print? Like, how are you putting that in?
The outside numbers, are you referring to like what's in purple or?
The yellow, so, or the yellow green. Like, are you, like, how are you adding the numbers to multiply in? Or is that just keeping track of the count?
Oh yeah, it's just keeping track. We're not multiplying anything.
Okay, thank you.
Yeah, this is to try and help visualize what's happening at each step.
The only pattern I'm seeing is that you're summing up people. So like if you put a number above each person is kind of how I'm visualizing it in my head. The first person that enters the room, he's number 1. The second person that enters the room, he's number 2. Third person's number 3, and so on. And you're just summing up those numbers. So 3 plus 2 plus 1. 4 people go in. Well, now you're going to add 4. So 3 plus 2, 4, 5 plus 1, 6 plus the new person. He's represented as number 4. So that's 10. That's all I'm seeing right now.
But that is the pattern though, isn't it?
I guess.
However you want to like phrase it, whatever words you use, if you see the pattern, that's the goal. And once you reach that, you can start to work from there to create your formula.
Oh, should that last handshake be 5 on the bottom there? Handshake's 5.
Oh yes, good catch. That is a typo. I should fix that. Very good catch. Thank you. But yes, once you are able to uncover the pattern, you really just want to break down, or you are able to break down that pattern into a recursive formula. So like we've taken the two elements of our problem here that we see at every step, at every iteration of the case, and we are able to articulate them in layman's terms, in words. And from there, we can structure it into a pattern that makes a little more sense, right? So we take the yellow, green, and the purple, we add together. That's our return statement. And you can work from there, backwards from there, into your base case to create a working algorithm. All right. Any questions on that? Okay. Just a quick recap. Here's another way of visualizing it. We color code in a slightly different way. Basically, because it's a recursive function, each purple, I guess, part of the equation in this case is color coded into something else. So yellow is when there are 4 people in the room. We basically add that to blue, which is when there are 3 people in the room, which is added to turquoise when there are 2, which is added to green, which is when there are just 1. And that gives us our total of 6 handshakes between the 4 people. And again, it's not an exact science, so don't get too caught up trying to find the exact base case. This is the exact same example, but with a base case of 2. Really, what base case you start with is the only impact it has is how your algorithm is going to look. And yes, this could be a very big impact because if you choose a base case that's too complicated, it could be simplified even further, and that's not a very good way to start. But for the most part, the point here is there is flexibility. All right, let's go back to the Fibonacci sequence that Phyllis walked us through at the start of class. If we were to try and visualize it, this would probably be what it looks like before Phyllis started indenting the different iterations. And when we start to indent the different iterations, we might see something like this. And from here, we could kind of break down, just the way we did before, what it really looks like if we were to, like, let's say, de-abstract each component at each step. Fibonacci 4, because we know that Fibonacci is the addition of the previous 2 numbers, is going to essentially be the Fibonacci sequence of 3 and 2, whereas 3 is the Fibonacci sequence of 2 and 1, and that takes us all the way back down to Fibonacci 2 plus Fibonacci 1. And that will take us to our base case where if n equals 0, we return 0, or if n equals 1, we return 1. Okay, that looks like a duplicate slide. Okay, factorials. You all did factorials. Yeah, that's one of the challenges. So this is, what is this illustration? It's just, yeah, it's just a visualization of how factorial would work for the first 4 numbers. We could see visually here that we've got like a pyramid structure going on. If we were to solve this the imperative or iterative way, this is the solution. It would be n times n minus 1 times n minus 2 all the way until we reach 1, which really is our base case. So this works, except it's not as clean or elegant as a recursive solution. With recursion, we could condense it into just these two expressions, I guess, or elements of an expression, and we are able to reach the same conclusion. So iterative solutions are step-by-step. They utilize loops and conditionals, and we rely on variables to help us build our solution as we go. But with our recursive solution, we use the technique of starting with a base case, and the variable that's passed in is the variable that's also returned. Any questions on any of this? I've got some really cool resources here to share with you all. I really like this video. Again, I guess it's because I like visualization. Let's wait till this dude goes away. Oh no, I just clicked and it gave me another ad. Yeah, if you still need to wrap your head around recursion a bit more, this is an amazing video. One of my favorites. The way that he visualizes these different algorithms. I actually have a YouTube subscription as well. It's just, I don't know, for whatever reason, I guess because I have to sign into Platoon, I can't use it here. So yes, you all can watch this video and some of these other ones without ads, thanks to your subscriptions. That's a really good one. There's also some really fun ones in here. This dude is amazing. He is an engineer. He came up with a coding language called Rockstar. Let's see, where's that section on Rockstar? Well, actually, let me just pull it up. Rockstar coding language. And it's a computer programming language designed for creating programs that are essentially also hair metal power ballads. Basically, all of this is code. And it's kind of ridiculous and absurd how he does it, but this is a fun video. He talks about how he went ahead and did that, and there's a section where he talks as well about John Conway's, there it is, Game of Life. So really cool video. It is an hour long. It's from a more ancient era of when keynotes were very long. What else? We've got a few more videos on expressing the game of life, and we have a fun video here about taking a recursive concept and creating a game out of it. So I'll share this in the class Slack, and from here we can break. We are going to, let's go back to slide 1 and let's talk through today's schedule. We're pretty much on track. We are going to take a break. I'll open up breakout rooms. Everyone should jump into the first challenge, which is the group challenge. And once you all solve that, you could stay in your breakout rooms and work on the remaining challenges together. We'll hop back in at 11 o'clock to do our weekly retro. I think you've only done one weekly retro so far, right?
Yeah, I don't think we did one for the first week. But yeah, the second week.
Okay. And when you did the last one, did you do it at 11 o'clock or did you do it at the end of class?
I think we did it at the end.
Yeah, that sounds familiar.
Okay. I'm not picky about when we do it. If you all want to do it then, we could do it then as well during stand down. We'll just meet like half an hour earlier instead. So yeah, I'll change that a bit and I'll share the screen for when you all get back from breakout rooms. But yeah.
So after lunch, are we going to go to week 4 then? Is that the...
No, after lunch is just more working time. So
Okay.
I'll open up well, I guess breakout rooms will be open the entire time, but yeah, you're all free to take your lunch and then get back to working on the rest of the challenges. And then I'll change this so we will reconvene at 3:30-ish, 3:45. We'll do the feedback form, and then we'll have a retro, and then we'll do a stand down with some demos from today's challenges. Sound good? Cool. All right, with that, I'm going to stop the share, cut the video, and we can break.
So are we doing the flat